In this video, I look at some ideas within Chapter 7 and work through some problems. These are essential skills for having success on these topics on the next test. I think on your next exam, there's going to be about 8 to 10 questions that are coming from Chapter 7. And I think if you master the ones that I list here, I bet you're going to get at least 6 to 8 of those questions on the next test. They're going to be easy for you. I think these are things that we absolutely have to take away from Chapter 7. I guess if you look at it from the other direction, if you're not able to turn these into easy skills, you're going to really struggle on the ideas on Chapter 7 in the next test. So I've provided a worksheet that looks at representative exam questions from Chapter 7. So tell me, why are you here watching this video? I'm happy that you are, but I'm curious. Have you already worked on this assignment? Were you able to answer some of the questions? And if you weren't able to answer them, were you able to get started? Do you understand some of the ideas? If you found weaknesses, did you already try to address those? Perhaps returning back to the e-text, looking at the videos I've shared. Did you already try to address your weaknesses or not? In Chapter 7, we really have to know our way around the periodic table. We need to have a periodic table that we can use to quickly determine the electron configuration and be able to analyze it for different features. So as you work through this video, having a periodic table handy will help. The first topic of effective nuclear charge, we want to be able to understand it conceptually, and we also want to be able to do calculations involving effective nuclear charge. The number of protons is given the symbol Z, and S refers to the shielding electrons. Our simplest approach for determining those are to count electrons that have a smaller principal quantum number as shielding electrons. This leads to some patterns on the periodic table. The effective nuclear charge increases as I move left to right on the periodic table. I think you should be able to explain that. I think your explanation will include the fact that you're increasing the number of protons, but you're not changing the shielding electrons because you're moving across in the same principal quantum number. A secondary effect is if you move down a column, the effective nuclear charge increases slightly. That's not nearly as important as our trend left to right, but I think we need to be aware of it. Going down a column, the effective nuclear charge increases slightly because the shielding electrons are said to be more diffuse, which means more spread out. There are less effective shielding. So we have this dominant relationship left to right and a smaller one as we're going down a column. So let's see how we can answer some questions with this information. These two examples here, they're involving ranking and effective nuclear charge. So in this question, I have to make sure what is the property that I'm looking at? It's the effective nuclear charge. Ranking them, a really common question format. So if I'm going to determine the effective nuclear charge for hydrogen, it's easy, it's +1. There are no shielding electrons. For chlorine, I want to make sure that if I'm considering the valence electron, that's the outermost electron, which is in a 3p. I have a total of 10 electrons that have a smaller principal quantum number. We're being asked to determine the effective nuclear charge for a sodium cation. An ion can still have a valence or an outer electron. And notice in that case, the only shielding electrons are the 1s2. Because when it becomes sodium +1, it now has a total of 10 electrons. And that turns out that that one has the larger effective nuclear charge. So that would be my particular ranking. In terms of question number 2, if I use the formula, I find that the effective nuclear charge for helium is +2, and I have +1 for either hydrogen and lithium. So now something else must be going on. The something else, this involves going down a column. This would be then my resulting value. So notice within here, these are not simply using the periodic table and looking at a single relationship. They're combining ideas, and that's a typical approach that I'd expect for your exam. Here's 2 more on the same subject. When I'm looking for the valence electrons in bromine, calcium, and carbon, I can easily calculate the values here for the carbon and the calcium. For bromine, I'm choosing that as an example because I wanted to point out that given the electron configuration, the 3d10 are also counting as shielding electrons. In question 4 here, we also have to be able to calculate the effective nuclear charge, not just for a valence electron, but for any electron. And in this case, we're looking at electrons that are in the 2s atomic orbital. And we're comparing that for sodium and for carbon. So if we write out the electron configuration, it's the same strategy. We're looking for, as shielding electrons are as ones that have a smaller principal quantum number. And we can use this information to now calculate the effective nuclear charge for the 2s electron in these. Here's another one where we're not simply looking at the valence electron. Really typical format. We're considering the 2p electrons that would be in chlorine and xenon, and then also the valence electrons. If I'm looking for the 2p electrons, they're going to have the same shielding. They'll have the same number of electrons that have a smaller principal quantum number. But xenon has more protons, so right away I know that the effective nuclear charge would be greater for the 2p electrons in xenon. And in terms of the valence electrons, it's +7 for chlorine, +8 for xenon. So this would be an example where neither are true because they're greater in both cases for xenon. So in terms of the effective nuclear charge, what questions do you have? Do you still have concerns that I haven't addressed with these examples? Are there some types of questions easy for you and others more difficult? Give me some input, please. When we're looking at the size of atoms and ions, I want to know the trends and be able to explain them. I know that as I move down a column, I'm increasing the principal quantum number, n, for the outer electrons, so my atoms are getting larger. And as I move left to right, I'm increasing the effective nuclear charge, which causes a contraction. I also know for ions that the anions are always larger than the neutral atom and cations are always smaller. This idea here of looking at the principal quantum number, that's a really important skill when we're looking at rankings involving size. And when I say rankings, here's very typical exam questions. Ranking in each of these cases from the smallest in size to the largest. I chose these examples because I was trying to illustrate different things. For the first one, I see a combination of anions and cations, and all of those are isoelectronic. They all have the same number of electrons, but they have different number of protons. That makes me it allows me to easily put together a ranking. Same number of electrons, but more protons would make it smaller. How about that next set? Give that next one a try if you have not yet done so. Within my analysis here, I can quickly compare magnesium and calcium based simply on differences in the principal quantum number. Calcium is going to be larger, magnesium will be smaller. When I think about the corresponding ions as +2, I again can now think about how the cations are going to be smaller. And I can also think about how the one with the smaller principal quantum number will be smaller than the one with the larger principal quantum number. When I put together these different ideas, well, I know magnesium is smaller than calcium. That was based on the principal quantum number. Cations are smaller than their neutral atoms. So right away, I would be able to place 3 of them right there. I know the magnesium 2+ is smaller than magnesium, which is smaller than calcium. How about placing calcium 2+ within this series? Well, the calcium 2+, that's isoelectronic with argon. Argon was already smaller than magnesium because it's in the same row. And I know that the calcium 2+, that's going to be even smaller than argon. So by putting together these different ideas, this would be my corresponding ranking. Notice how this question was not just tell me the direction an arrow goes on the periodic table. It's combining various ideas. If I think about the next set, I can consider the neutral atoms, nitrogen and oxygen, and I know that they get smaller as I'm going left to right because the effective nuclear charge is increasing. I also know that the anions are larger, much larger. And I have two examples, the nitride and the oxide, that are isoelectronic. Putting those together, this would be my ranking. Give that last one a try. What would be your reasoning? Here's the different things I know in terms of these relationships. I know that helium is smaller than hydrogen. It has 2 protons instead of 1, and they're both in the 1s atomic orbital. I know hydrogen and helium are both smaller than lithium. They have a smaller principal quantum number. I know the lithium plus cation is smaller than the neutral lithium atom. And when I think about lithium plus, I know it has 3 protons and it's 1s2. Information like that, I find making a little sketch of what the shell picture would be like, that helps me organize that information as well. Putting together the different features, this would be my ranking. Are there aspects of any of these that you're unclear on? When it comes to the size of atoms and ions, what questions do you still have? Are there some that you can do and some that you can't? Share your questions. For the electron configuration of ions, we'll be making either anions or cations. Key thing within here, the key mistake that I see students make is when it comes to our cations, we want to remove electrons from the atomic orbitals that have the higher principal quantum number. And this means we have to be careful with the transition metals. Here's a few applications. When I add an electron to fluorine to make it fluoride, it will then have 0 unpaired electrons. For zinc 2 plus, zinc 2 plus is 4s10, 3d10, 3d10, 4s2, excuse me. I'm going to remove 2 electrons from the higher principal quantum number. That's the 4s2. So when zinc becomes zinc 2 plus, I see that I have 10d electrons. When I'm looking at the electron configuration for chromium 3 plus, I'm going to start out and ask, well, what is the electron configuration for the chromium atom? This is one I got to be a little careful with. It has an anomalous electron configuration. If I think about those in order based on the principal quantum number, I would put the 4s1 being highest in energy, and I'm going to remove a total of 3 electrons. Leads me to the argon electron configuration, and then 3d3 after that. Most students do well looking at the electron configuration of ions. Back to the questions of what can you do, what do you find difficult? I know the main stumbling block here is looking at the transition metals when they become cations. Ionization energy, several thoughts within here. We want to be able to write the corresponding equation corresponding to the first or the second or any successive ionizations. Recognize that they're always endothermic. The smaller size corresponds to a higher ionization energy. So factors like the effective nuclear charge and the principal quantum number, those are what we'd want to attend to. This is a really good way of explaining why it's a large value for hydrogen and even larger for helium, because those are quite close to the nucleus. Those are quite small elements. It explains why if I then go to lithium, it's larger, it's easier to remove the electron. I see a trend then during the contraction as I go from lithium to neon. A few exceptions along the way that I can also explain. How the 2p is a little further than the 2s. How when I'm considering in the orbital diagram for nitrogen and oxygen, I have the electrons paired up in the same atomic orbital in oxygen, leading to heightened electron-electron repulsions. Another idea is successive ionization, how it always increases, it's always a higher ionization energy as you remove the first, then the second, then the third electron, because we said that that leads to a smaller and smaller ion, and that there's a large disproportionate increase when we're removing from the inner shell electrons, because those are much smaller. And we could think about data like that that shows the successive ionization, for example, something here like carbon, where we can remove 4 electrons. After we remove 4 electrons, we are now to the inner electrons, and how that there's a much larger ionization energy corresponding to removing those last 2. So here's some example questions. Select the equation describing the third ionization of boron. This would be my best description. I can remove 1 electron, that's the first, remove another, that's the second. This is removing the third to make it boron 3+. And I'm also being careful to make sure it's describing gases, because that's the definition for ionization energy. Removing an electron from the element or ion in its gaseous state. This one, which of these figures would best represent the successive ionization energy for an alkaline earth? So what I'm looking at pattern-wise here, in this one I see that they're trying to say they're all equivalent and then it goes up when you're removing the 4th electron. Or there's a steady rise and then it goes up removing the 4th. 2 different plateaus, or a steady rise and then it's much more for removing the 3rd and the 4th. So right away, I'd rule out these first 2 because it's not a plateau as you remove the 1st and the 2nd. There's always a steady increase. I think this is the best answer for an alkaline earth where you can remove the 1st electron, you can remove the 2nd electron, and then it's much higher in energy to remove the ones that are closer to the nucleus. These are asking for which has the largest second ionization energy. Comes back to, well, which of these then would be smallest? The ones that are smallest have the higher ionization energy. So the first one involves nitrogen, phosphorus, fluorine, chlorine, that region of the periodic table. So I'm thinking among these neutral atoms, fluorine would be the smallest. And after I've removed an electron from each as +1 cations, fluorine is still the smallest. It would have the largest second ionization energy. It would have the largest first ionization energy. The second, which of these has the largest second ionization energy? I have to be a little bit more careful here. I think my choice is down to sodium and neon, because the reason I'm saying that, well, argon's definitely the largest is larger than neon. It has a larger principal quantum number. When I'm thinking about the sodium and magnesium, I'm thinking about the second ionization energy. When I remove the first electron from sodium, now it has 10 electrons. When I remove the first electron from magnesium, it has 11. They're in different principal quantum numbers. So I'm thinking to myself, the 2 that are most likely to be smallest must be the ones, either sodium or neon, that are in n equals 2. If I then look at the corresponding effective nuclear charge, I see that it's a little bit larger for sodium plus than it is for neon plus. That tells me that the sodium plus is going to be a little bit smaller, and sure enough, it has a larger second ionization energy. So when it comes to ionization energy, a couple different skills. We were identifying the equation, we were looking at successive ionization energy, and we were seeing connections within how ionization energy pertained to size, and that allowed us to make predictions. What questions do you still have on the topic? Electron affinity, this refers to the energetics of adding an electron. We're interested in where the electron is going to be going, not where it initially is. And I mean that where it initially is, that's what ionization energy involves. With electron affinity, we ask the question, well, where is the electron going to be going when it's being added? We see that the values can be either negative or positive. What does the sign tell you? What does a negative electron affinity mean versus a positive one? Negative means that it is favorable to add the electron. It's an exothermic process. And the greater the attraction between the atom and the electron that we add to it, the more negative that electron affinity is. So what would lead to a greater attraction? If we add the electron and it's close to the nucleus. If we add the electron and it experiences a large effective nuclear charge. What would reduce the attraction? Well, if I'm pairing it up with electrons that are already in the same orbital, I'm trying to put a negative with a negative, that's unfavorable. Now, these particular factors, many times they're competing. More than one of these is taking place at the same time. So it doesn't lead to the same clear trends that we saw with ionization energy. But I think we can use these insights to explain the values that we have. Why it's positive for some like noble gases and quite negative for the halogens. So in terms of the noble gases, I'm adding an electron to a higher energy orbital that's farther away from the nucleus. If I add an electron to helium, it has to go into the 2s atomic orbitals. This is back to this idea, where's the electron going? So for helium, it's initially 2 protons, 2 electrons. I'm going to try to add the electron. It's going to have to go to a 2s. It goes to an entirely new principal quantum number. If I think about it in terms of the effective nuclear charge, for the electron that I've added, well, it's further away from the nucleus than the ones that were initially there. It is shielded by both of those. It experiences no net effective nuclear charge. That's why it's unfavorable to add to helium or to the other noble gases. For the alkaline earth, those are also positive because now we're adding not to the same atomic orbital as far as a 2s or a 3s. We're adding it to the corresponding p orbitals, which we know are a little bit higher in energy. They're further away from the nucleus. So it turns out those are positive values as well. How about nitrogen? Well, within nitrogen, this would be its orbital diagram. To add in another electron to nitrogen, okay, I'm at that example where I'm pairing up 2 of them in the same atomic orbital. That's going to be unfavorable. Sometimes students ask, well, what about the pattern below that? Why would it be favorable to add to something like phosphorus? Well, with phosphorus, those same atomic orbitals, instead of being 2p, they're 3p. They're larger in size. So even though I'm pairing up 2 electrons, they're in a larger atomic orbital, and that makes it so it's not quite as unfavorable. With the halogens, within there, in each of the cases, very exothermic, very, very favorable to add an electron to a halogen. It's true that I'm going to have to pair them up with an electron that's already in the same atomic orbital, but they have really high effective nuclear charges acting on those. So evidently that's what wins. That's what makes the process exothermic. One more idea is adding a second electron to an anion. That's always unfavorable due to electron-electron repulsions. Adding a second electron to oxygen, it's exothermic to add the first one, but not the second. After all, if I have this -1 anion, to add a second electron, I'm trying to add a negative to a negative. That's not energetically favorable for that particular anion. So a few questions. This one's back to the idea, can we recognize the correct equation? So within this one, what's the second electron affinity for hydrogen? What I'm trying to point out here is that electron affinity, it refers to adding an electron to an atom or ion in its gaseous state. It's not referring to molecules. So when it says hydrogen, it's thinking about the hydrogen atom. The second electron affinity is the second electron that I've added to make it hydrogen 2-. Within this one, based on what I just said, at the level of the atom itself, this would be very endothermic. It's not going to be easy to add a second electron to the hydrogen atom. Here's a series of questions. First one, which of these elements have large exothermic electron affinity values and also large exothermic ionization energy values? It's combining both of those ideas. If I'm thinking about a large exothermic electron affinity, well, I know that applies for the halogens, but the ionization energy is always endothermic. So none of these would be largely exothermic in both of those characteristics. The next one is talking about the factors of what would lead to a exothermic electron affinity. I think it's when the electron is added and it experiences a large effective nuclear charge. Strong attraction for the electron that's being added. I think the other choices there are all unfavorable in terms of adding the electron. within the last one, which of the following has the most exothermic electron affinity value? I think it's going to be adding it to the fluorine atom. In fact, that's the only exothermic example that I list here. I think it's endothermic to add an electron for the other three choices. Do you agree with that? Can you explain why it would be endothermic to be added to a nitrogen atom, a neon atom, or the oxygen minus anion? So for electron affinity, notice the style of the questions were a little bit different. We weren't necessarily making predictions. We were a little bit more in the category of offering explanations. So what's your view on electron affinity? What questions do you still have? Wrapping up then, I think these are essential skills within Chapter 7. Coming back to this idea, Chapter 7, probably about 8 to 10 questions on your next test. Which of these do you still feel like you need to work on a little bit to master? If we can make these easy, that's going to be great as we head into the next test. Have you mastered these skills? If not, which ones do you think you still need to work on?